Saxon Advanced Mathematics, Lesson 11. We have two topics today. We're going to talk about circles, review a little bit of vocabulary, cover a few basic principles, properties of circles, I might say, and then we're going to switch to an algebra topic that I know you're going to love. So, let's start out with a little bit of art. Sounds good, right? Flipping pages. Okay, let's draw 5 little circles. These are words that I know you've heard many times before, but some of them are quickly forgotten. I know some of them aren't. If you start at the middle of a circle and you draw a line anywhere straight from the center to the edge, that's called the radius. Fun fact, more than one are called radii. If you draw a line going from edge to edge that doesn't go through the center, that's called a chord. That's one that people forget. Here's one that most people remember. If you draw from the edge to the edge through the center, that's called the diameter. And that's the word that whenever my teachers in grade school would say, I always thought they were going to call on me because diameter sounds like Diane. And I would always get a surge of adrenaline because I thought I was being asked a question. Fun fact. Okay, like a chord, but one that passes through and doesn't just stop at the edges of the circle, but one that continues, this is called secant. Now, here's the way my mind works. See how these two are very similar? One stops at the edge and one goes through. This one always reminds me of guitar strings over the opening, right, in a guitar. Right? Those are the strings of the guitar. That's a 5 string. I should give it one more. So it's a 6 string. There. I always thought because these look more like guitar strings, this should be called chord because that's a musical word, and let this one have the weird name of secant, but it's not like that. And that's always, I've held it against these words forever, but chord does not go with the one that looks like guitar strings, which I think is just a darn shame. This one is fun. This one is where we have a line that goes and it touches just at one point. Now my picture is not as perfect as it needs to be to show a perfect tangent. But the other thing that's cool is that you can draw a line from the center to the line and it makes a right angle. It touches exactly at one point. This is called a tangent. Secant and tangent are trig words that we're going to, that you already know quite a bit about. Don't let the comparison, don't try to build a comparison in that. That'll just hurt your head. The cool thing about the word tangent is, you know how people sometimes say, oh, I was talking to this person about pickles, and then we went off on a tangent about kittens. You know, it's like there's a point where the conversation's connected, and then you just took off on the other one. Like this is the conversation about pickles, and here's the point where you were talking about pickles and kittens, and then there's where it took off into just kittens. I love that we have a math concept that really kind of matches with the common use of the word tangent. Yay! Interesting. Okay. That's the center of the circle. Sometimes we have an angle that comes out from the center, and it looks to me like a Pac-Man, but we call it a central angle. I mean, I call it a Pac-Man too. And what's helpful about that is that we remember that the Pac-Man is taking bites out of the circle, right? This area right here is what we call the intercepted arc. Right? It's the amount of his bite. In a central angle where you have a cute little Pac-Man, these amounts are the same. If that's a 30-degree angle, then the intercepted arc is also 30 degrees. They are the same. Contrast that, if you will. I just taught this lesson to the Algebra 2 peeps. Sometimes we have something that's not a central angle. It's called an inscribed angle. And this, to me, looks like a Teenage Mutant Ninja Turtle. Exactly. It's profile view, right? His eyes right here. There's the knot. There's his scarf. The little ends hang down there. Teenage Mutant Ninja Turtles are far more complex creatures than Pac-Mans. And accordingly, if you have a... Let's go to the same inscribed angle. They also have inscribed angle, intercepted arc, sorry. The pink thing is the intercepted arc. And let's say it's the same. Let's say this is 30 degrees. A Pac-Man does not have, this isn't 30 degrees for him. This is 15 degrees. Ah, interesting, right? Which means that if you know this number, you cut it in half to find this number. If you know this number, you double it to find that number. Make sense? Sort of, kind of? Here's another picture. This is what we call an inscribed quadrilateral. And I'm trying to make it look random because it can be random. And here's a cool thing about these. Let's say that these are the 4 angles. Right? This is called an inscribed. The word inscribed means written within. Quadrilateral. We're going to use all of this information to do the problem, so don't be mad. Angle A plus angle C add up to 180, and angle B plus angle D add to 180. That will always be true in these angles. Weird, right? But that I could explain it to you. It has to do with the inscribed angles. But just trust me on that. All right? And I have one more picture to draw. Well, no, I have 2 more. And then we'll get to our problems. How about a circle with 2 segments inside, 2 chords, if you will, right? They're not guitar strings. What if we know, not the angles, but we know the lengths? That's a cue. The lengths of these segments, of these vertical angles, are proportional. Ready? X over Y, the 2 pieces of the same line, right? One part of the segment over the other part of the segment equals, oh wait, this is not how I wanted to write it. Never mind. Multiply times each other. X times Y equals P times Q. You multiply the 2 pieces of the same chord. Who would have ever known, right? That's true. And then we have one more. And this one's complicated, so I'm going to draw it big. And honestly, I don't know that we have problems that... Now look what's going on here. There's an inscribed angle, and here's another inscribed angle with the same bite. Do you see how I did that? This is angle A, this is angle B. These 2 angles have to be the same because they both have the same intercepted arc. Does that make sense? See that? We know it's 2 times angle A, and we know it's also 2 times angle B. So that tells us that A must be equal to B. Weird, right? We can also find proportions. I want to do it back on this one though. This is where we're talking about 2 angles lying on top of each other. Over here, I could also do x over q, which is one segment over the other segment equals p over y. I'm not sure that's helpful. This is better. I like this better. Don't worry about that. I told you, but you don't really need to know. And then the last part has to do with tangents. Let's say we have a circle. Let's say that there's a point outside the circle and there's a tangent coming off the circle and connecting at that point. What's interesting is that it will always have this form. Then we'll have a radius and a radius that are going to the point of the tangent, right? This will form right angles. That will bisect it. What in the world? And M will be equal to N. The length of this side will be equal. We're going to see this shape later. I don't think we see it in these problems coming up. No, we don't. But just keep in mind, there's a weird thing. If you do a point outside the circle and then send two tangents to hit the circle, it creates this beautiful proportional thing. All right, enough talking. Let's do some problems. Example 11.1. We have a circle. And I see a bunch of angles in here. It goes like this. Whoa. A, B, P, and R. Now, as I sit here looking at this, I realize, oh, A is an inscribed angle. B is an inscribed angle. P is an inscribed angle. And R is an inscribed angle. And they match up. They do that overlapping thing, right? Where A and B look different, but they both have the same intercepted arc. So A and B must be the same. Same thing for P and R. P makes this intercepted arc, and R hits the very same points. So P and R must be the same size. Oh, I'm just thinking about this and getting it all straight in my head. Okay, so let's start marking some angles. This is 46 degrees. That's random, huh? This is 30 degrees. It's getting crowded in there real fast. Down here, this is x plus 10. And John's writing it just the way I did. He's writing it outside, and then he puts a little arrow like that. And then this one is y plus 20 degrees, and he draws a little arrow like that. And then, yeah, he named the angles on the outside. Find x and y. All right, as I was drawing it, I saw what was important. Angle A and angle B both have this intercepted arc, right? B goes from there to there, and A goes from there to there. We don't know how big that intercepted arc is, but we know what angle A is, so we know that angle A must be equal to angle B because they have the same intercepted arc. We know that angle A is equal to 30 degrees, and we know that angle B is equal to y plus 20 degrees. And so we can set those two things equal to each other, right? We can say 30 equals y plus 20, and subtract the 20. Y equals 10. That's not a geometry answer, so we don't need to put degrees on it, right? But it tells us it's an algebraic component of that. So this is right. Yay! Do you feel smart? You should. Now, how about what's going on with this? That's y, so now we need to figure out x. We've got the same situation going on over here. We see angle R is an angle that hits this intercepted arc, right? Because he goes from there to there. And then we see angle P hits the same points. So we know the same thing. Angle P equals angle R because they have the same intercepted arc. So angle P equals 46 degrees and angle R equals x plus 10 degrees. So we can put those together and say 46 equals x plus 10. Subtract the 10 and we get x equals 36. And again, it's not degrees because that's not the actual measure of anything, but x is an algebraic value of 36. Yay, we got it right. I went out of order that time, right? I did the y first and then the x. So you'll see sometimes it works out just fine. It's just a question of what you're looking at first. I found it easier to look at A and B first, but it's just what jumps into your head. No worries. Okay? My tip is if you can't think of what else to do, try looking alphabetically. Example 11.2. Another pretty picture. I hope you're in the mood to draw today. These quadrilaterals are wonky. When we draw an inscribed quadrilateral, they don't have to be perfect. In fact, they're supposed to not be perfect. All right, and I remember that the deal here is that the opposite angles add to 180. So I'm just going to write that down. I don't want to forget. All right. I've got a bunch of numbers. This is x and this is y. Okay, this is 50 degrees and this is z degrees. Okay, we're supposed to find x, y, and z. All right, let's go alphabetically. All right, we know this. We know that the opposite angles have to add to 180. So x plus 80 have to equal 180. So x equals 100. That's pretty clear, right? Yay, that's right. Y plus this one have to equal 180. So we subtract 75. I'm not even going to write it down. Y equals 105. And in these cases, these are both the angle measurements, so we can put degrees on those. All right. I feel good about it so far. Now, how are we going to figure out z? Well, z is this intercepted arc up here, right? It goes from here to here. That's kind of hard to deduce when you're starting these problems, but that's what John's trying to say, is that z is this intercepted arc. And so we can go, oh, okay, well, let's see. 80, if we look at angle that's marked as 80 degrees, that goes from here all the way up to here, right? So z is going to be equal to that angle times 2 would give us the whole intercepted arc. That will be equal to z plus 50, right? The whole pink intercepted arc has to be 60 because it's, or 160 because it's double we take the 80 and double it, right? To get all of that, we know part of it is 50 and the rest of it is z. Now we just do algebra. And I'm not even gonna swim that fish. That's just so straightforward. We can do it in our brains. And again, that's a degree measurement, so we can put a degree sign on it. Is it right? Yay, it's right. These are kind of fun, don't you think? Not too hard. And I like having a little bit of algebra in there. I will let John get away with his crazy geometry problems as long as we can do a little algebra. Here comes another one. This time we have a skinny little ninja mask, and there's a straight line there, which looks very weird. X, Y, and Z. All right. This is 35 degrees, and this is 75. All right, well, let's look. We've got some inscribed angles here, so let's look for their intersected arcs. This, I'll color the whole thing in. This angle has an intercepted arc here. So that is Y. So that tells us that Y must be equal to 2 times 35, or 70 degrees. That wasn't so bad. Let's try X. X is this intercepted arc, and we can see, oh look, that matches up with this angle, right? So X is twice of that, so that must be 150. Yay. Z is our last one. And we can see, well, let's see. Z is this. And that would be related to this angle. But we don't know what this angle is. So there's 2 ways we can do this. We can either figure out what this angle is, which wouldn't be that tough because these 3 have to add up to 180, right? So it's 180 minus 35 minus 75. This is 110. So this must be 70 degrees. And then we double it to get 140, right? That would work, right? We can just calculate this angle, and then it's another inscribed angle, so we double it to get the intercepted arc. But the other way we could have done it is to just say these 3 have to add up to 360. This much is 220, so we need another 140. So if you remember that all 3 of these have to add up to 360 because they go all the way around the circle, that would be another way to get it. Whatever fits in your brain best. Those are all correct. Yay! Oh, Lord have mercy. There's 2 more. 11.4. Circle. Vertical lines crossing on the inside. We have no information about angles. We've got segments. Okay, we multiply together the 2 chunks of the same chord. So, and they will be equal to each other. So, 15 times x plus 10 equals 20 times x plus 5, right? And we had the formula for this back on the other page that we saw to do that, like that. So the 2 pieces of the same thing get multiplied together, and they're equal. So now all we have to do is multiply. 15x plus 150 equals 20x plus 100. Let's swim the 15x this way, and then we'll move the plain number the other way. Cancel, cancel. and we get 50 equals 5x. X equals 10. Yay. No degrees in this problem, so we don't have to worry about putting that on our answer. Okay? So that's how we can use that one, that idea to solve problems. Here comes one more. And it's based on that last picture that we did, the tangent one. So there is a problem using that one, but it's pretty easy. The triangle and the circle are tangent at 3 points. Okay, this is how it looks. There's a triangle like that, and then there's a circle. Oh gosh, pretend it's perfect. Okay. And those little bits are each x, that like these little bits there. This is 10, right? Ideally, these are touching at just 1 point. This segment is 6. This segment is x plus 4, and this is x plus y. All right, what we remember is that when you have a point outside the circle and you have lines drawn from that point to two different tangents on the circle, these lengths will be the same. So that means that this x plus 4 and this 6 must be equal to each other. And then conversely, over on the same side, this x plus y and this 10 must be equal to each other. And then these two x's are equal, but that doesn't really do us much good, right? So we're looking at this point to the tangents. These two segments are equal. And from this point to the tangents, these two are equal. So we can just do two quick little equations. We better do this one first because that has two letters. So we do x plus 4 equals 6. X equals 2. I hope you agree with me on that one. That's pretty fast. And then we can plug that in over here. It would be 2 plus y equals 10. And we get y equals 8. And these are the correct answers. Okay? All right, that's enough geometry. More than enough. Now we're going to turn our attention to the quadratic formula, aka man-eating dragon. Remember that, I'm not going to write it all again, I'm just going to show you. A couple days ago, we were talking about completing the square. And we were saying that when it comes to quadratic equations, there are 3 ways to solve them. If the numbers are easy enough, we can just look at it and figure out what multiplies to that and adds to that and write them down. That's cool. But sometimes the numbers are too complicated and we can't just see it. So a sure-fail method is completing the square. And we went through all of those steps. And that's the problem with it, is there are so many steps. So the math dudes of the 1700s said, can we build a shortcut? Can we cut through all of those steps and just leapfrog into the answer? And this is what they came up with, this cool little quadratic formula. And we're going to remember again how they devised that. We're going to do it in just a minute. But now we're focusing on this. So this is the 3rd way to solve a quadratic equation. It works for everything, just like completing the square works for everything. Quadratic, you can't go wrong, okay? So even if it is a super easy one that you could have solved by inspection, there's no harm done in doing quadratic or completing the square for that matter. All right, so let's look at how these dudes came up with the quadratic formula. They started with this. And they said, let's not even put numbers in. Let's just use the letters and solve it for x, and then we'll have a formula. So what they did was they followed the exact same steps for completing the square. They started by dividing away that lead coefficient. Right? And I think it was with you guys. I forgot to do that, right? I left the 3 there for completing the square. So that's what I'm remembering to do now. We divide away the a. Now we have x squared plus bax. And then let's, in one step, let's kick this guy to the curb. Okay? Now we need a magic number. Magic number, we take the b term, which is actually b over a. We multiply it by 1/2, which is the same thing as dividing it by 2. We draw a little arrow here, and then we square it. That is going to be b squared on top over 4a squared. Ugh, that's a disgusting magic number. But okay, fine. So let's write it here as well, plus b squared over 4a squared. Looks good, right? We added the magic number in both places. Now let's write our perfect square. And I'm going to do it the slow way. We know that this is going to be x plus, and we know the arrow tells us what goes in here, b over 2a. It's getting kind of scrunchy. I hope you can read that. Now let's test it and make sure it works. We should multiply these together to get that, and that works because it's b squared. The 2's make the 4, and then the a's. And it should add to this. Yeah, because it would be, the denominators match, so we would add it together. It would be 2b over 2a, and then we can cancel the 2, so it becomes just b over a. All right, now I'll write it in its squared form. That side's all cleaned up. Now we need to fix this. The denominators do not match. So we have to multiply this side by 4a over 4a so that we'll get a 4a squared in the denominator here, right? So this looks good. I'm going to multiply that, but I'm going to change the order. I'm going to put the b squared first, and then I'm going to do minus 4 times a times c. And this is all over 4a squared. I'm starting to get excited because this is looking real good to me. I like the way that looks. Okay. Next step, I'm going to deal with that. Let's square root both sides. And I'm going to scooch it over a little bit just so I have more room. X plus b over 2a equals plus or minus the square root of b squared minus 4ac, but I notice that my bottom is a perfect square. So I don't need to leave that in the pig house. I'm bringing it out as a 2a, right? Square root of 4 is 2, square root of a squared is a. So he's out of the pig house now. He's free and clear. Now I'm ready to do my last step of subtracting. X equals minus b over 2a plus or minus the square root of b squared minus 4ac over 2a. And the very last step that makes it perfect is we can push these together into one fraction because the denominators match. Ready? Here we go. X equals minus b plus or minus the square root of b squared. Oh, I'm sorry, that was a minus and I changed it into a plus for 0 reasons. Minus 4ac all over 2a. And there he is, our little quadratic wunderkind. And we made him, we did it. We just started with the basic standard form, and we followed the steps for completing the square, and we got the quadratic formula. Now we can use this whenever we want to shortcut this process and find our answers. So let's just review how to do that. How many of these are we gonna do? Just one. Oh, it's so fun. I could do lots of them. This is example 11.6. Use the quadratic formula to find the roots of the equation. Remember that expression, roots of the equation? Just means solve for x. And here it is, 3x squared minus 2x plus 5 equals 0. So the first thing we do is we check to make sure it's in standard form. X squared, x, plain number, equals 0. Beautiful. We want it to look like this, right? Everything's in order and it's all on the left side. Beautiful. Now, so that's step one. Put in standard form. And you know, sometimes John tries to be cute and he'll mix that up. Second step, find A, B, and C. Now, finally, it's okay if we have a number in front of our x squared term. It's perfectly fine. 3 minus 2, remember the sign matters, and 5. All right. Third step, set up the quadratic formula with buckets. Please, 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 always use buckets on this, because I'll show you why. Let me write the formula one more time. Make sure you get this in your book somewhere. Make sure you have the standard form. This definitely, you want to memorize all of this. Any formula that you have to use in math, you need to commit to memory. Sorry. Okay, there it is. So here's what I mean by the buckets. X equals minus that. Right, so I'm, for every place that there's an A, a B, or a C, I'm setting up a bucket so that I can pour these values in and then simplify. It is so important when you have a formula that has minus signs in it, you need to use buckets. You can get away with it if your formula is only adding. It's less tricky, but if you have minus signs in your formula and you potentially have minus signs in your values, please don't even waste your time not making buckets. Okay, B is minus 2, so that goes there and there. A is 3, and C is 5. Gracie's wagging her tail in her sleep. Good girl, Sue. Good girl. She's having a happy dream, I'll tell you that right now. All right, so now we've got everything plugged in. I like to clean up the radical first. Minus 2 quantity squared is 4. Minus, oh boy, 4 times 3 is 12, times 5 is 60. That's minus 56. Huh. All right, well, we can deal with that. So now I'm going to rewrite x equals, now this can go to a positive 2, plus or minus the square root of minus 56 all over 6, right? 2 times 3. Now this needs work. First of all, I know I can break this number down and bring some pigs out. I know this is 8 times 7, so it's 2 times 2 times 2 times 7. And I know I'm going to break this out as an I. So there will be 1, 2 on the outside, right? A pair of pigs on the inside makes 1 on the outside. Left on the inside are these guys, so that's 14. And then I have an I to take care of the minus sign. Oh. All right. I'm good with that. And it's all over 6, right? And now I see I could factor a 2 out of the top and cancel that against the 6. So I'm going to do it the long way. It's okay if you do it in your head, but I want to make sure you understand exactly what we're doing. We are not just canceling here. We are mentally factoring out the 2. Right? We pulled the 2 out of both terms. Used a 1 as a placeholder here. Don't need a placeholder there. Now we can cancel 1 and 3. And our final answer is x equals 1 plus square root of 14I over 3. Oh, I forgot this should be plus or minus. I just dropped that. I had it right there and then I dropped it. Guess what? Oh, that's the right answer. John just does one more step to make it super pretty. Remember that when we have complex numbers, we always want to keep that really strong A plus BI formatting. We want to separate these fractions. So we want to write it as x equals 1/3, the real number component, plus or minus square root of 14 over 3I. We can float the I. I know, it just creeps me out, but that is the prettiest format because we're showing that it's a complex number. Dun, da, da, da. That is the final best answer. Really love that format. Really love the clean, strong, complex number presentation of real number and imaginary. That's why we float it, is because we're saying this whole thing is imaginary. If we plunked this I up closer to the square root of 14, it just sends a different message. It isn't as clear that this whole piece belongs to the world of imaginary numbers. It's of a different realm, let's be honest. I always forget to finish my steps. Set up the quadratic formula with buckets and then simplify. Simplify and solve. Let's throw both of those S words in. All right, hopefully this is bringing back warm and fuzzy memories of all of your quadratic explorations last year. And you feel like it's an easy review, all right? Super, super, super important. When people like mathy people, think of what do students learn in algebra? Solving quadratics is one of the biggies. So you are tackling the heart of the subject. All right, I'm done talking. Thank you. Goodbye.